Welcome to ATMOS 5000, Day 9. Today we're focusing in on Chapter 3, Section 3.7 of the Stull textbook, with the topics being apparent temperatures like wind chill temperature and heat index. Apparent temperatures are a metric that was devised to try and describe how the atmosphere actually feels to an individual who is exposed to it. We've all been outside and understand that it feels much colder on a windy day and it feels much hotter on a humid day. But the actual temperature doesn't reflect those human conditions on how the conditions actually feel. So we devised these apparent temperatures in order to try and be able to accurately describe the impact that these weather conditions have upon the human body. The wind chill temperature is a metric that was devised to try and describe how cold somebody will feel when exposed to a certain air temperature and wind speed combination. It is an apparent temperature, and if the wind chill temperature is below zero but the actual temperature is above zero, water that is left outside will not freeze because the actual temperature is above freezing. So you have to be careful when using the wind chill because it's really only responsive to how people feel to a given set of environmental variables. So here we have an equation for wind chill. It's essentially a constant 0.62 times the temperature of the air minus 13.1 degrees C plus another constant of 0.51 times the temperature of the air minus 14.6 degrees C times this ratio m over m naught raised to the 0.16 power. And so m naught is a reference wind speed of 4.8 kilometers per hour, which is about 2.6 knots almost. And the m is the actual wind speed. So for m greater than this reference speed, then we have a definition of a wind chill temperature. And if the wind speed is less than your reference value, then the wind chill temperature is defined as equal to the temperature of the air. In this slide, we have a graphical depiction of the wind chill temperature as a function of the wind speed and the actual air temperature. So you can see that the wind chill temperature is always equal to or less than the actual air temperature. And you'll also notice that the biggest change in the wind chill temperature occurs when the wind speed varies between 0 and 10 kilometers per hour. And as the wind gets even faster, the slope of the wind chill temperature line changes and doesn't change quite as rapidly. So you can see that for a combination of minus 20 degrees Celsius and 20 kilometer per hour winds, you're looking at a wind chill of about minus 32 degrees Celsius. And wind chills below about minus 48 trigger essentially a warning for human health, and anything less than minus 55 is considered extremely dangerous, where you can get frostbite by having exposed skin out for only just a couple of minutes. The heat index, in contrast, is trying to describe how we actually feel on a hot and humid day. So why do we feel hotter on a humid day? And it has to do with the ability of your body to evaporate water. So when we sweat, that's our body's mechanism to try and cool off. And it's the evaporation of that sweat that requires energy, which removes heat from our skin surface. And if the atmosphere is saturated, then there's no evaporation, and we do not get that cooling from the evaporation. So the heat index, temperature of the heat index, equals the TR, which is this reference value of 0.8841 times temperature plus 0.19 degrees Celsius, plus our temperature minus this TR, times the relative humidity divided by 100 times the saturation vapor pressure, E sub S, divided by ER, which is a reference water vapor pressure. So what we're looking at here is the saturation vapor pressure, E sub S, is a form of the Clausius-Clapeyron equation, which shows what the water vapor concentration is at saturation as a function of temperature. It's an exponential function. And then, so we have a relative humidity, which is on a scale between essentially 0 and 100. We divide that by 100 to get essentially a number that is less than 1. So we're multiplying that times our E sub S over ER. And that whole quantity is raised to the P power, which is 0.0196 degrees per degree Celsius to the -1 times temperature plus 0.9031. So here is a graphical tabular representation of the heat index, which is an apparent temperature. And what you'll notice is that the actual air temperature of, say, 20 degrees Celsius, and when the relative humidity is less than 60%, then it actually feels cooler than 20 degrees C. And you'll notice that at 20 degrees Celsius air temperature, the heat index never deviates very much from that. And that's because at 20 degrees Celsius, there's really just not much water vapor in the air, even at saturation. But if you contrast that with, say, 30 degrees Celsius, and you have a 80% humidity, then you have increased your heat index temperature to 37 degrees Celsius, which is a sizable increase. But where this really kicks in is by the time you get up to 35 degrees C, so now we do have a warm day, and if you have 35 degrees C and 80% relative humidity, the heat index is 52 degrees Celsius, and I guarantee that nobody will be very safe under those conditions, and you can suffer heat stroke rather quickly under those conditions.